Okay everyone, this is problem 3.15 out of Griffith's Introduction to Quantum Mechanics. And it says, prove the famous, your name, uncertainty principle relating the uncertainty in position, A equals X, to the uncertainty in energy, B equals P squared over 2M plus V. And it should equal this expression here. And it asked why for stationary states this doesn't tell us a whole lot. So to begin with, the main equation we're going to be using is our generalized uncertainty equation, which will look something like sigma A squared sigma B squared is greater than or equal to 1 over 2I times I h bar, your expectation of your commutation relation divided by m, and this is all squared. Okay, so the main thing that we need to find to be able to create this uncertainty relationship, or find the uncertainty relation, is the commutation relation between x hat and p hat squared over 2m plus v. So real quick, I think this was actually maybe a problem in a different, this section, but one of the things we're just going to prove really quick as an aside is this. And I don't know if I uploaded this problem already. I believe this is a problem in Griffith to prove this commutation relation. Sometimes I get a little lazy with the hat parts, but hopefully you know that I'm working with operators. So we're going to prove this really quick, just so that we can write our commutation relation in this form. Okay, so just doing the left-hand side, that's the same as A times B plus C minus B plus C times A. So this is AB, and then I'm going to distribute this one, minus BA, and then AC minus CA, which of course is exactly what we have here. This part is the commutating relationship between A and B, and this is A and C. Okay, so we proved that really quick and easily. So now what we can do is apply that to the problem we're working on, since it's of the same form. This can then be expressed as x p squared over 2m plus x and v. Okay, and that'll make this problem a little easier. So in the first hand, we have x p hat squared over 2m minus p hat squared over 2mx, and we'll get plus xv minus vx. So these will go away, and this was the benefit of writing the commutation relationship, is that we can really just focus on the x and p, since x and v commute with each other. So I'm going to just write this. I'm going to factor out a 1 over 2m, and we'll have x hat, p hat, that's what p squared is, minus p hat, x hat. Okay, and now what I'm going to do, 1 over 2m, is I'm going to add and subtract the same quantity inside our parentheses here. So what I'm going to do is, I'm noticing we have an xp here. So if I had a pxp here, that'll actually be very useful, because if I factor out a p hat to the right, I'll have xp minus, should be a minus px, which of course is a commutation relationship. Now, obviously we have to add this same quantity here to make this equal. So hopefully that actually works with what remains, which is ppx. And in fact it does if we pull out one of our right x's. So we'll do that right now. So 1 over 2m xp minus px, we factor out a p to the right, and then over here plus, we'll have a p factored out to the left, we'll have xp minus px. And of course this is just xp, and this is just xp. Okay, so we have 1 over 2m times this commutation relation plus p x hat p. Now the commutation relation xp, it's given in the book, and in fact we've proven this in a previous problem, I believe, 3.5 I think it was. So it's pretty easy to rederive if you want. You just give a test function f minus f, and then just remember p hat is minus I h bar d by dx. If you want to rederive that, you can, but at the end of the day, this is equal to I h bar. Okay? So this commutation relation is 1 over 2m times I h bar p plus p I h bar. Now I and h bar are just constants, so that derivative that is in our p operator, it's not really going to do anything because they can be factored out. So this is just going to be, you'll get a 2i h bar p hat, that 2 will cancel here, so you just get I h bar p divided by m. So now we can plug this into our equation for our uncertainty between a and b, which has to be greater than or equal to 1 over 2i times I h bar p all over m. And this is all squared. Obviously the I can drop there, and you'll get sigma a squared sigma b squared equals h bar squared our p operator squared all over 4m squared. And then just taking the square root of both sides, you can get your well, this should have been an inequality, my bad. You can get your uncertainty of h bar over 2m, and then the absolute value of our expectation of momentum. Now for stationary states, of course, the expectation value for momentum is 0 because it's the same thing. We've proven this as well, the derivative of x position with respect to time. So if x is not changing, then the expectation value of momentum is just 0. so you don't really get anything out of that. Okay, that's everything. Hopefully that helped with this problem. If it did, please give me a thumbs up and subscribe, and I'll continue to post more solutions out of some undergraduate physics textbooks.